Hello friends, we are beginning with our assignment on the external flow problem of a flow past a square cavity using OpenFoam open source software, which is presented by Nitesh and Manish. So let's understand it. The external flow problem of a fluid dynamics is a fascinating and complex area of study, offering insight into the intricate behavior of fluids as they interact with solid bodies. In this particular investigation, we delve into the dynamics of flow past a two-dimensional object featuring a square cavity. This scenario holds a practical relevance in numerous engineering applications ranging from aerodynamics to heat exchanger designs. Now let's move to our next slide, which is we can see that model description. Now let's understand it. So in the model description, we can see there is a geometry. In this geometry, there is a square cavity which have a boundary with no slip conditions. And on the rectangular geometry, we can see at the top and bottom, we have a no slip condition. And at the inlet, we can see velocity at the inlet is 0 and u inlet is equals to 1, and at the outlet the pressure is 0 and the gradient of velocity is 0. Now let's look at the governing differential equations. The governing equations for this problem are the Navier-Stokes equations, which describes the motion of a fluid. First one is the continuity equation, dou p by dou t plus del dot rho v is equals to 0. And second one is the momentum equation in the x and y direction, which you can see here. Here u and v are the velocity components in the x and y direction. P is the pressure, t is the time. X and y are the spatial coordinates and r is the Reynolds number. Now we will move to our next slide. We will see the boundary conditions which we have taken in the problem. The boundary condition for the flow past a square cavity are typically no slip conditions on the cavity walls, which means that the fluid velocity is 0 at the solid boundaries, that is u is equals to v or is equal to 0 on the cavity wall. Now look at the inlet boundary condition. First one is the velocity inlet, specifying the velocity component at the inlet, that is v inlet is equals to 0 and u inlet is equals to 1. Second one is the pressure inlet, specifying the pressure component at the inlet, that is dou p by dou x is equals to 0. And now we will see the outlet boundary conditions. That is, first one is the pressure outlet, specifying the pressure at the outlet, that is p is equals to 0. This is a common when the outlet is far from the region of interest and the flow can be assumed to become fully developed. Now we have 0 gradient of velocity, assuming that the velocity gradient normal to the outlet is 0, that is dou u by dou x is equals to 0. To solve this problem, we will take help from the OpenFoam tutorial that we already have in OpenFoam. The nearest case to our problem is the cavity problem, so I have copied this to my dummy folder, created one new folder, that is OpenFoam. Now I will copy the cavity folder to this new folder. Now I will take out this file, that is physical properties, from the constant folder, and then I will delete the constant folder. I will make a new folder in OpenFoam, that is geometry, in which we will store the geometry and the mesh file. Open this geometry folder in the terminal, write gmsh command and open the gmsh. We are all set to make a geometry now. We will make geometry by bottom to top approach. So first we will draw the points and then we will join them. The first point that we will draw
is the 0 0 0, where all the 3 points are at 0, and the another one is at 20 comma 0. Third point we will make at x 20 and y 10, and z will be 0 again. And the last point, fourth point, we will make at y equal to 10 and x 0 and z also 0. These points that we have drawn here, we can also check these points in the script. So as we can see, the point 1, 2 and 3 and 4 are there in the script. So we will save it and then minimize. Now we will join the points that we have. To make a line, click on the starting point and the ending point and then press E. You will get your line. The rough geometry of a rectangular domain is ready now after joining all the 4 points. So now we will make a square inside this rectangular geometry, for which we have to again make 4 points, and after that we will join all of them. The coordinates of the point number 1 is the x2, y4 and the z will be 0, and the mesh size at a point will also be 0. The another point have a coordinates x at 2 and y at 6 and z will be at 0 again. The third point will have the coordinates 4 and 6, and the last and fourth point will have the coordinates as 4 in x and 4 in y. We have a square inside a rectangle. So to make this a surface, we will click on plane surface and then select the surface boundary. Since we have to analyze the flow of the fluid inside the domain, so we have to make it as a solid. To extrude, click on the extrude button and then translate. Select the plane surface and write a unit length in dz and then extrude. Now open the script and update it. In extrude, below the surface, one layers and another is recombine. After saving, now we will give names to our surfaces and the volume. Select the inlet surface after writing inlet in physical surface context. After that, write the outlet and select the outlet surface. Similarly, select the front and back and top and bottom as a surface. From physical groups, select the volume and now select the volume from the extruded geometry. If we see this script now, after reloading it, we can see all the surfaces and volume written in the script. Now we will generate the mesh in 1D, 2D, and we can see it also in 3D. As we can see that mesh is quite coarse right now, so we will have to make it more finer. To make it more fine, in this script we will write 0.1 in place of the 1, that is the mesh size we have given to each point. After this, when we reload the script, we can see the mesh, which is quite abnormal. Problem here is that I have put a comma instead of a point, so that's why the mesh is like that. So after correcting the mistake, the mesh should be okay. So now when I generate the mesh in 1D, in 2D, in 3D, it takes a little bit time, but now we can see the mesh is much more finer than that we have earlier when the mesh size is 1 unit. In bar above, we have an option called as tools, in which we have the another options: general, geometry, mesh, etc. From these options we can see the surface labels, curve level labels, etc. And we can also change the color of mesh and some another settings of the mesh from here. Now as our mesh is ready, so we will save the mesh and we will export the mesh in the .msh file. Since I already had this file with the same name, so I will replace it. We have to change the format also, because the OpenFoam only works with the version 2 ASCII, so we will change it to this option. Our geometry.msh file is ready now. To the format that OpenFoam can read, we will open the terminal and will write gmshToFoam and the file name. This will generate a constant folder again that we have deleted earlier, but this time this constant folder will have the some more files which have the data of our geometry and mesh. We will place the physical properties file back to the our constant folder. In polymesh folder there is a file named as the boundary. We will open it. Physical type patch is written in this file, so we will remove this line. After removing this line, change the type of the front and back from patch to empty. In top, change type from patch to wall, and in inlet let it be the patch, and in outlet let it be the patch also, and in bottom and square change type to the wall. Copy text from here as we will need it in the pressure and the velocity file that we have in 0 folder. Save the file and come back to the cavity folder. Open the 0 folder and then the pressure. Paste the copied file here and then remove those two lines below the type. Script is already written in the pressure file, so it will help us to guide in the editing this file. So we will copy the 0 gradient and will paste it in all the walls, that is top, bottom and a square. Since we know that there is no slip on the walls, so velocity there will be 0. So when there is Dirichlet boundary condition for the velocity, there is a Neumann boundary condition for the pressure, so that's why here we have written 0 gradient. Outlet would be the fixed value, that is uniform 0, so we will write it in the outlet. After editing this file, remove the files that we had earlier in the pressure folder, which helped us guiding in writing the script further. We will copy it as it will be helpful for us in the velocity file. In velocity file, paste the copied text. Now change the 0 gradient at top to the no slip and 0 gradient at the bottom to no slip conditions. Also in the sphere, change zero gradient type to the no slip. The outlet here will also be zero gradient, and the inlet we will have the velocity in x direction, which is 1, and in y and z direction velocity will be 0. Front and back will remain empty. Remove the extra text and check that we have written the right boundary conditions here. Everything seems to be fine in boundary conditions. So now we will open the control dict file. From control dict file we can change the delta t or the number of time steps. Also we can change the stop and end time. First we will run it only for 0.5 seconds. Open the terminal and write checkmesh command to check that mesh is fine. And we do not have any error in the mesh. Mesh seems to be okay. So now we will type icoFoam. So after writing icoFoam, the solution is being generated. It will take some time. As time is going on, we can see that some new folders are being created in our cavity folder. These new folders create the data or the properties at every time steps. Run Parafoam command in terminal. This will open the Paraview, and after you apply, you can see your domain here. This will only run for 0.5 seconds. You can see how flow is going on, how velocity is varying. Now we can increase the time for which our simulation will run. So for that we have to go into the control dict file, and we will change the end time from 0.5 second to 50 seconds. And after saving this, we will again run the icoFoam in terminal. It will take a much longer time since there are too many time steps here. I will open Paraview parallel to see the results.
Now let's talk about the solver scheme we have chosen and why we have chosen them. The first one is the DDT scheme. The term DDT stands for the differential delta time. Selecting the DDT time derivative scheme is essential for accurate temporal discretization, influencing the time stepping accuracy and stability in transient simulations. This means that the default time discretization scheme for the simulation is Euler. The Euler method is a simple and explicit first order time stepping scheme. Now we have chosen the next scheme, that is gradient scheme. Choosing a gradient scheme is crucial for accurate and stable numerical simulations. The selected scheme impacts the discretization of spatial derivatives, influencing solution convergence and accuracy. The default is Gauss linear. This line specifies the default gradient scheme for scalar field other than pressure P, and the grade P is Gauss linear. This line specifies the gradient scheme specifically for the pressure field P. After that, we have chosen the divergence scheme. In the divergence scheme is essential for accurate fluid flow simulations. In this, the default none, the line specifies the default divergence scheme for scalar field other than velocity field, velocity field. The chosen scheme is none, which means that by default no divergence term is included for fields other than the velocity field. After that, we have chosen the Laplacian scheme. Choosing a Laplacian scheme is crucial for accurately modeling diffusion process in fluid flow simulations. This scheme influences the discretization of Laplacian term, affecting the numerical stability and solution convergence. In this, the default is Gauss linear orthogonal. This line specified the default Laplacian scheme for scalar field. The chosen scheme is Gauss linear orthogonal. This typically implies a linear interpolation using the Gauss method with an orthogonal correction for the Laplacian calculation. After that, we have chosen the interpolation scheme. Selecting an interpolation scheme is vital for accurate representation of variable across mesh elements. This scheme influences how values are transferred between neighboring cells, impacting solution accuracy and stability. In the line 41, we have it is default linear. This line specifies the default interpolation scheme. The chosen scheme is linear. This means that the linear interpolation will be used by default when interpolating values between mesh points. Then at final we have used SN grade scheme, which at line 46 is default orthogonal. We have chosen this SN grid surface normal gradient scheme is because it is crucial for accurately capturing gradient at cell faces in boundary regions. This scheme enhances accuracy near boundaries such as walls by considering the surface normal direction. Optimal for simulations where boundary effects are significant, improving precision in capturing flow gradients along surfaces. And it is default orthogonal. This line specifies the default scheme for calculating surface normal gradients. This chosen scheme indicates that the default method for computing surface normal gradient is orthogonal.
To check the mesh independence, we will change the mesh size and then we will compare it with the earlier size that we had. For that, we will open the script and then we will change the mesh size in it. Earlier we had mesh size of 0.1, but this time we will decrease it to 0.09 at each and every point. After saving the script, reload the script and generate the mesh for 1D, 2D and 3D. It will take some time to generate the mesh, and now we can see that our mesh looks finer than we had earlier. I will skip the intermediate steps since all of these steps in between are same as that we have done earlier. I will directly open the Paraview. I will make plots for velocity and pressure on a line. After feeding the dimensions and applying that, we will get the plots of velocity and pressure for this mesh of 0.09. Save the image of plots. Generate the same plots for mesh size of 0.1. Keep in mind that dimension you are taking for line earlier must be same as that of this. We can also see the line that is generated over here. From load state option that is in file, we will open the both the plots. To see the plots on a single graph, we will click on line chart view. To make the plots visible, click on the I button that is in Pipeline browser in front of the plot name. To differentiate between the plots, we will change the color and the names of the pressure and the velocity. Make change in colors of velocity and pressures. For mesh size of 0.09, pressure we will designate by P2 and velocity we will designate by U2. For better visibility, make sure that you change the colors also. Plots for both the mesh sizes looks quite similar, but if we zoom in to some extent, we can differentiate between them. But this is the negligible amount of change in velocity and pressure. The properties are not changing with the mesh size, so we can say that our solution is the grid independent. We have done this analysis for a straight line at an particular instant, but we can do the same analysis for longer period of time. For this, we can use plot data over time from the filter option. Since my system is not much powerful, so I will just show the glimpse of it. This is the velocity and pressure at a point that is varying over time. Properties looks like they are making a wave.
Let's analyze the flow around the square cavity. In the main flow channels, you will observe streamline that represents the primary flow paths. Near the boundary, due to no slip conditions, we can see the low velocity, and away from the boundary we can see high velocity. Here the streamline typically move smoothly along the length or width of the cavity depending on the direction of the applied pressure gradients. In the velocity vector will be aligned with the streamline, indicating the direction and the magnitude of the fluid velocity in the main flow channel. Near the corner of the cavity, you will often see the formation of the vortices. Streamlines will curve and circulate around the corner, forming vortex structure, and the velocity vector will show the rotational pattern around the corners, indicating the presence of corner vertices. In the region where the main flow impacts the cavity wall, you can see streamlines changing directions and forming recirculation zones. And for the velocity vector will show reversed direction in this recirculation zone, indicating the backflow of the velocity vector or stagnant region. And now if the Reynolds number is high, we can observe flow separation from the cavity wall, where these streamlines detach from the walls, and subsequently these streamlines may reattach as the flow moves around the cavity. Now for the velocity vector, we can see the separation and reattachment point with high gradient in velocity near these regions. Now let's look at the central region of the cavity, especially for the lower Reynolds number. We can observe smoother streamlines with less pronounced vortices. And for this velocity vector in the center may indicate relatively uniform flow with lower velocities compared to the main flow channels.
To calculate the lift and drag forces, we need to add some text in our control dict file, which is in system folder. So for doing that, there are two ways. We can find the text from the OpenFoam help, or the another way is we can also find that text from the tutorial files that we already have on our OpenFoam. Now we will search for the text that we want. So we will open the terminal, and here we will write a line which says that in the foam tutorial folder there is a file known as the control dict, and in that control dict file we have a keyword that is force. So we will search for this. We have this much of files that have this keyword in these folder. The text format that I need is at this highlighted location, so I will copy that location, that system folder to desktop. CR here means copy recursively this file to designated folder. Copy the required text format from the control dict file. Paste this text in the control dict file of our problem. Remove the unwanted text. We will make some changes in this format. Change the reference area to 2 and reference length to 1. Change the name to square and also change the density to density of air, that is 1.209. Add p name to p and u name u. Change the name to force coefficients and save the file. We need to add some more text here. For this, now I will search for forces. I will use the same way, but this time this text will be in some another folder. We will open the highlighted location and copy the file to desktop as we have done it earlier. Now copy the text under the functions and paste it above the force coefficients. Change the name from wings to square. Also change the density and make some other required changes. This time when we run icoFoam to get solution, we can see that some extra terms are being calculated here. For example, cm, cd, cl, etc. And this data is being stored in the newly created post processing folder inside the square folder. We can see the values here. Calculate the lift and drag for different Reynolds numbers. We will change the velocity and then we will calculate the CF and CL for them. We will change the velocity this time to 3 meter per second. Earlier it was 1 meter per second. Change the magnitude of velocity in the U file, that is in 0 folder, and we will also have to change the magnitude of velocity in the system folder and control dict file. Now run icoFoam in terminal and calculate all of the coefficient.